Hello everyone and welcome back. Today I'm gonna talk about time travel in Marvel's Endgame. Tony Stark in the movies were famous to develop time travel in the quantum realm. But how so? How did he do it? Well, it happened in the quantum realm. And they expected us to believe it that in quantum universe, time behaved differently. Well, this is true. But time doesn't behave differently only in the quantum universe. It also behaves differently in the macroscopic universe as well. Take Einstein's relativity for example. It says that if you move fast, closer to the speed of light, or if you go near to the black hole, time slows down relative to an observer on Earth, or relative to an observer waiting you while you are going at the speed of light. So, what makes quantum mechanics, quantum universe so special for time travel to happen, according to them, of course? Well, there's something sensible about their discussions. Well, they first talked about quantum fluctuations. Let's discuss that first as well. So, imagine a smooth space. If we are explaining this in a macroscopic world, we have to use Einstein's general theory of relativity. And it assumes that in a delta bound, in a smooth manifold that is so small that it can be taken as Minkowski space. If you don't know the meaning of these terms, just imagine. We are on Earth, right? We are so small creatures relative to the magnificent size of the Earth that we believe for centuries, as humans, we believed that Earth was actually flat. But this isn't the case, as we all know it. But relative to Earth, we are so small that we assume that Earth is smooth. And this is exactly what the mathematical argument technique says us as well. So, in the end of all this argument, what I'm trying to say is that in macroscopic universe, all of the spaces are actually smooth manifolds. But if you go to quantum realm, what happens is Heisenberg's famous commutation relations. So in quantum universe, you don't expect to explain the system fully. By fully, I mean in classical terms. In a classical system, you have several, let's say, attributes that you give to the system. For example, if you are explaining, let's say this is classical, this is quantum. For the classical system, in classical system, you have particles. These particles have positions, and they also have velocities. But in a quantum realm, these have to satisfy commutation relation. We call this Heisenberg's uncertainty principle. If you know the position of a particle very well, you don't know its velocity as precise as you would. This means that you would lose information by knowing some other entity. This, first of all, is something counterintuitive for us. And because of our inability to capture this system fully, our universe constantly fluctuates. And in the quantum world, there are fermions and bosons, especially fermions, create antiparticles. And this antiparticle creation happens spontaneously and constantly. And this happens in a time scale that is so small that you wouldn't be able to distinguish, the creation and the annihilation. And if one could decipher the view of this quantum manifold, it would look like something like this. It would be constantly changing, and you would only see the peaks and the, let's say, lowest parts of it. So it would be like looking at a, let's say, it would be like looking at a distorted television. This would be like that. So what I'm trying to say is that they are trying to capture this inability of time. They are trying to capture time travel in a quantum realm by saying that yes, we don't know anything about the quantum system, so it needs to satisfy some relations. And this relation, this commutation relation of Heisenberg's, can be extended to particle's energy and how the particle experiences time. So there is a commutation relation between energy and time. So if you know a system's energy in a quantum level, you wouldn't be able to tell how time ticks that well. This is something, again, controversial, as it would look for a given system. If you know the time's precision so well, then it would look like that your system actually, in some cases, it would look like it wouldn't follow conservation of energy. But I mean, for all cases, conservation energy holds, but this is something technical that I won't go in detail here. So, if you can engineer something in principle by giving it energy that is so much, you could actually disrupt how well a system can track its temporal dimension. But we have a final clue in the movie where Tony Stark, just before he develops and engineered his idea, he drew something we call as Mobius strip in topology. So, topology is the field in mathematics where one studies geometry without distances. This kind of explanation seems so abstract, and it is. Topology is a very abstract field, but it has some applications and realizations in geometry. And Mobius strip is one of the primitive examples given in an introductory topology course. So, Mobius strip is something like this. And you can create this yourself by taking a rectangular strip of paper and by gluing one side of the paper to the other and by giving it a twist, because you glue one side of the paper not to the, let's say, normal, like if you glue one part, if you glue the top of this to the bottom of the other part, it would be just like a circle. But if you twist it and glue it like that, you would actually observe that object you created has only one side. Because if you begin the movement, if you imagine yourself as a miniature ant and move on that object you created on this Mobius strip that you created, that is three-dimensional, you would actually see that just by moving, you would actually come up to the same side of that object. But this wouldn't happen. So it is as if the two sides of the rectangle have united in this shape, and this is actually what happens. But you give it an additional twist, and this additional twist in quantum mechanics is related to something we call as Berry phase in condensed matter physics. And this Berry phase and this twist and the movement of it, and like moving away from your starting point and coming to the same point, but changing an attribute of your initial vector. In this case, since you move through, as you move through the manifold, the curvature of this Mobius strip, if you hold a stick, you would observe that while moving on the strip, when you come back, the vector that you started with would show into the opposite direction. This would mean that there is an element in your system that could track your movement, your spatial dimension. So your system isn't actually memoryless. So there's a memory in your system. There's a way to calculate if you moved from your starting point to the end point. And this is something important because it gives you a navigation. It gives you a way to measure whether if you moved or not. But if you want to build something like this, in order to create time machine, you would have to create something that is equivalent to Mobius strip in a temporal dimension. Meaning that this Mobius effect should be not in a spatial dimension as I explained to you, but should be in time. And how can this be in quantum mechanics? Well, maybe if you combine these two principles I just explained to you, if you can, by giving energy to the system, can somehow manipulate the system's ability to capture time with this navigating system. One might be able to devise such a, let's say, machine. But is this something feasible? I don't think so. Because how can you manipulate space-time? How can you build, let's say, this kind of structure to time, specifically in quantum mechanics? It's a very hard thing to even imagine, because in quantum mechanics, you have flat space-time, so it's like Newtonian mechanics. So it's not like, you don't work on curved space-time, so you don't get those funny effects in those Penrose diagrams of black holes. So it's very hard to imagine what Tony Stark was thinking, and it's probably just a caricaturization, so it's not something real, of course. But thinking even slightly on these topics, I think, is important. And time travel, although it is something taboo in physics, actually, because I mean, if you are talking about time travel in physics, people are generally think that you are going crazy. So, but I mean, I think it's important to think some novel ideas all the time. So thank you for your time and stay with physics.